Hello, welcome to the DL Software Digital Guide, a one-stop practical guide for DL software toolkits. This is part of the DLView video series that show you how to make best use of DLView effectively. In this video, I'm going to show you how to solvate a system by using a range of solvent templates that are included in the DLView software. This demonstration assumes you understand the basic operation of DLView software. If you have not run DLView before, I would recommend you to watch the first DLView video titled Ready, Get Set, Go. The content of this video are as follows. Firstly, I'm going to show you how to use the solvating feature contained in the control file based on some examples of input configuration files. Secondly, solvent templates contained in the solvent directory will be briefly mentioned. Thirdly, the use of counterions should you wish to set up an electrically neutral system. I'm going to solvate two structures from the examples directory. The first one is a single ascorbic acid molecule, commonly known as the vitamin C. The second one is the superoxide dismutase protein enzyme that is encoded by the SOD1 gene. Okay, let's start with ascorbic acid. This structure can be found in the example directory in DLView software. When using the solvating feature, any structures supplied as an input file will be considered as the solute by DLView. We are going to use the CVFF for the force field model and solvate the input structure with the tip 3P water model in a 40 Armstrong cubic system. To solvate a system, DLView will use one of the predefined solvent templates specified by the user. These are located in the solvent directory. What you see are a collection of file names of different solvent templates. The solvent list is a text file that contains the information about these solvents. Note that the available solvents are classified into different categories, such as water, alcohols, nonpolars, and so on. Each solvent is assigned with a unique key followed by a brief description such as the name of the solvent and the force field scheme from which the template was derived. This is followed by the file name of the template. For instance, we intend to solvate the ascorbic acid with the tip 3P water model. The key we would need to use in the control file is tip3p_o, and the water template file that DLView is going to refer to is shown here. Let's look into the tip3p water template file. A solvent template file is consisted of pre-equilibrated pure solvent molecules at the standard density at 300 Kelvin in a cubic box of 20 Armstrong in size. The solvating process involves the replication of the template box into the user system and removing those solvent molecules that overlap with the solutes according to the cutoff distance specified. Should the size of the user system model is not in the multiple of 20 Armstrongs, the replicated solvent boxes at the edges will be truncated. Now, I have already done the necessary changes to the control file for this demonstration, and these are shown as follows. First of all, I have selected the CVFF for the force field scheme. Then, I use the existing file for the ascorbic acid structure from the examples folder. Make sure the solution maker feature is switched off. Note that although the name it implies, there is a difference in using the solution maker feature and the solvating feature to set up a solution model. The solution maker feature is specifically used to replicate the molecular structure from the input file according to the user's specification. After that, you have the option to solvate the resulting duplicated system. In our case, we are interested to solvate the molecular structure as is from the input file. After that, I have defined the cell vectors of 40 Armstrongs along the X, Y, and Z axis to create a cubic system. Finally, insert the solvent key for the tip 3p water model here. If you do not wish to solvate the system, put the word none instead. This will deactivate the solvation feature. Note that the value 1.9 is the cutoff distance in Armstrong. This means any solvent molecules of which the atoms are located less than the cutoff distance from the solute will be rejected. Let's run DLFew. First of all, the program reads in the input structure and sets up the force field model for the solute. After that, the whole system model will be solvated with the tip 3p water model by duplicating the solvent template into the system. Once the program run is completed, a DL-poly field file will be produced as usual. The first part shows the force field parameters for the ascorbic acid, which is the solute. The latter part of the field file shows the tip 3p water model has been added. Here, I have used the VMD Visualizer program to show the structure of the resulting config file. The single solute molecule is located right at the center of the box, surrounded by the water molecules. Note that since the solvent templates were systematically duplicated in the system, some forms of orderliness are apparent and you would need to carry out equilibration runs in DL-poly before collecting the samples. You can also easily change the solvent molecule, provided the template of your choice is available and the force field scheme of your choice contains the necessary parameters to set up the solvent force field. Here, I have changed from the tip 3p water to ethanol as the solvent. The ETOH is the solvent key for ethanol. Now run DLFew again and look into the field file. You will notice the solvent has now been changed to ethanol. And this is what the config file produced by DLFew would look like. Let's solvate the SORT1 protein molecule. We are going to use the CHARM22 for the force field model and solvate the PDB input structure with the tip 4p water model in a 60 Armstrong cubic system. As usual, we begin this process by doing the necessary changes to the control file as follows. Once you have done the changes, run DLFew. Once the run is completed, you'll notice DLFew reports 3 warning statements. Note that, despite the warning statements, the DLFew file would still be produced. A warning is merely a notification that requires user attention to ensure the force field model that has been set up is what the user desires. To inspect these warning statements, look into the DLFew output file, which provides detailed reports of the structure conversion and model setup. To look for these statements, search the keyword warning that begins with a capital W. The first 2 warning statements were immediately located, which stated that a certain directive appeared in the PDB file which has something to do with the multiple potential usage. In this video, we are not going to discuss the multiple potential feature. Also, these warnings do not affect our fossil model setup. However, the third warning states that there is a net charge of -12 coulomb in the system. This is due to the fact that the SORT1 protein contained some charged amino acid residues. To set up a sensible model, the whole system would need to be overall electrically neutral. Usually, this is done by inserting counterions or opposite charged ions to counteract the net charge on the protein molecule. To insert counterions, go back to the DLFU control file and look for the counterion insertion section, as shown here. The value 1 means activate the counterion insertion process should the model requires. If the model is already neutral, then counterion insertion will be skipped. Otherwise, sodium cations will be added if the system is electrically negative, and chloride anions will be added if the system is electrically positive. The counterions will be placed randomly in the system so long they maintain a cutoff distance from the solutes. The cutoff distance in this case is 10 angstroms. Note that the counterions are inserted before the solvent molecules are introduced. This means the added counterions will also be regarded as part of the solutes in the system. Let's rerun DLFU and see what happens. Inspect the DLFU output file again, and you'll notice the warning statement about the charged system has now disappeared, showing the total charge is now 0. Finally, by looking into the view file produced, you will notice there are 4 molecule groups, the first 2 being the 2 monomers that made up the SORT1 protein. This is followed by the tip4p solvent model, and then there are 12 sodium counterions. That's it for this video session. I hope you enjoyed it. Please do explore other DLFU videos so that you can learn how to make use of the software. Thank you and goodbye.